Hello, everyone. Thank you for joining the first Geoscience and Geoenergy webinar of 2021. Happy New Year to all of you. We wish you all the very best in 2020. Sebastian and I are delighted, thankful, and grateful to all of you for supporting this initiative for good cause and to combat work from home isolation, connecting through this channel for an hour per week, and not only learning new subjects, but also share your questions, your comments about the topic that our keynote speakers are going to be addressing. Please do subscribe to our channel. We are delighted to have more than 1,700 subscribers to our channel, and we wish to hold a good community among all the interested researchers, scientists, policymakers, societal interesting people who would like to know about the role of or key role of geoscience and engineering in the society through this channel. Sebastian and myself are also grateful again to all our keynote speakers. We would like to also mention there is another initiative called Tea Time Talk Series run to allow junior researchers establish their professional network early at their career. Please do subscribe to their channel, volunteer if you are PhD or postdoc researchers to share your research with the broader community. Now to the first keynote lecture of 2020. We are delighted, pleased, and honored to have Professor Roland Horne with us today. Roland Horne is Professor of Earth Sciences at Stanford University and Senior Fellow in the Precourt Institute for Energy. He was also the chairman of the Department of Petroleum Engineering, which later changed to Energy Resources Engineering at Stanford University between 1995 to 2006. He holds all his degrees, BE, PhD, and MS, and Doctor of Science from the University of Auckland in New Zealand, all in engineering science. He's best known for his work in well test interpretation, production optimization, and analysis of fractured reservoirs, among many others. So far, he has supervised the graduate research of more than 50 PhD and 125 master students. He's an honorary member of the Society of Petroleum Engineers, SPE, and a member of the US National Academy of Engineering. He served on the International Geothermal Association, IGA, board for many, many years, and was the 2010-13 president of that association. Roland has been an SPE Distinguished Lecturer for many years and has been awarded the SPE Distinguished Achievement Award for Petroleum Engineering Faculty, the Lester C. Oren Award, and the John Franklin Carr Award. From Society of Exploration Geophysics, SEG, he received the Best Paper in Geophysics in 2011, and from SPE he received Best Paper in Journal of Petroleum Technology and Best Paper in SPE. The list goes on, and I can't do any justice to introduce his phenomenal impact in the community in geoscience and geoenergy community. He has also received 5 Best Paper Awards from Geothermal Resource Council, GRC. He's also a fellow of the School of Engineering at University of Tokyo and also an honorary professor of China University of Petroleum in East China. It's our pleasure and honor to host you, Roland, today. Thank you for graciously accepting our invitation to give this webinar. To the audience, please note, Roland's lecture would last for about 30 minutes, followed by questions and discussions. Like always, do type your questions in the chat box. Sebastian will chair the discussion session after Roland's talk. And also to the audience, please note, the lecture would be available for public for about 24 hours after this event, and it's gonna be off from the public access for about 6 months. and then later in summer it will be made publicly available too. So please do try to watch it. Those colleagues who will miss it, please ask them to watch it during these 24 hours, so that when it goes offline, we are going to have it offline for about 6 months, and then it will be allowed to be publicly released. So without any further ado, the stage bandwidth, the screen is all yours, Roland. Thank you once more for accepting our invitation. We are all looking forward to hearing your talk.
Very good. So thank you, Hadi and Sebastian, and all of those who you are attending remotely. The lecture I'm going to give you today actually is a distinguished lecture that I'm giving this year for the Society of Petroleum Engineers. And so I just want to let you know that this lecture program is supported by the SPE Foundation through Offshore Europe, as well as by the members of SPE and AIME. So my topic today is data analytics and machine learning in reservoir analysis. So the topic of machine learning, big data, is something which impacts us, all of us, every day in our daily lives. And here's a kind of a list of the kinds of things that we see in daily life. And to this list, I'll add one more, which is reservoir engineering. And that, of course, is my topic today. Before starting to talk about reservoir engineering, however, I'd like to pick out two of those other topics to emphasize some of the impact of, or some of the methods by which machine learning and data mining are used in reservoir engineering as well. So the two topics I'm going to talk about, first of them is machine translation, and the second one is self-driving cars. So machine translation first. Actually, the use of computers to translate natural language has been one of the targets of computer science right since the time when computers first appeared. And yet for decades, actually, computer-based translation was not very successful. And here's a classic joke which is told in the computer science literature about a translation of the phrase from the Bible, actually. But machine translation became successful in the last 10, 15 years or so, mainly because of a switch in the structural algorithms that are used for the purpose. The old kind of computer translation used to be rule-based methods that were sort of if-then-else rules and translating word for word, whereas the machine translation that we see nowadays is based upon data methods rather than rule-based methods. And examples that you probably use frequently are Google Translate, Bing Translate, etc. So here in blue is the topic. This is actually the abstract of what I'm going to talk about today, translated into Dutch by one of those data-based methods. And although I don't speak Dutch, those of you who do, I would predict, would find that this translation is perhaps not 100% accurate, however, sufficiently accurate for you to understand what it means. And down on the bottom of the screen, you can also see a simultaneous database translation, which is from spoken voice into English, and then actually from English into Dutch in real time. So the second topic I want to touch on briefly is self-driving cars. And in 2005, the so-called Desert Challenge, organized by DARPA, the US government basically, was completed for the first time and won by this particular robot car called Stanley, the one there in blue, which finished the course, which was 30 kilometers or so across the desert before all of the other vehicles. And what was significant about that at the time was it was, and one of the things actually, one of the particular ways in which Stanley differed from some of the other competitors in the race was that it was navigated based upon a data-based algorithm rather than a rule-based algorithm. So that was an early success. Now, the reason that they conducted a race in the desert, of course, is to make sure that nobody got hit by robots that were off course, etc. So for safety reasons, that's why it was held in the desert. However, if we move forward 10 years or so, this is a photograph I took on the streets of Palo Alto, where I live, on my morning commute. And we now routinely see self-driving cars actually moving around our town, not out in the desert, but in normal traffic with bicyclists, pedestrians, traffic lights, etc. Here's a second example, also on my daily commute. The real car on the right and the robot car on the left. And I added this slide. I took the photo too because I was intrigued by it. What you can see clearly in this picture, this is a T intersection. The real car is turning to the right, the self-driving car is turning to the left. They're stopped waiting for the traffic to move across in front. And what you notice in particular about the photograph is that both cars are actually disobeying the law. They're supposed to stop behind the white line, and yet both of them have gone forward beyond the white line. So importantly, that's sort of visual evidence, if you like, of the data-based approach. A rule-based method might be if white line, then stop, whereas the self-driving car has learned from the cars around it how to get visibility, etc., of the cross traffic. Okay, so let's get on to reservoir engineering, and this is the result of a slide, from a talk from this paper by one of my students, Jabs Al-Jubran, in which his actual topic was inflow control valves, but he was analyzing them using machine learning. And he wrote a small algorithm to scrape from one Petro, not just the titles, but actually learning from the content what the papers were about. And he was looking at the growth of interest in terms of SPE papers about inflow control valves and also about machine learning. And what you can see clearly from the graph, particularly the green part, is the explosion of interest in the energy industry in machine learning applications. And in the sort of the heat map, the black box, you can see the strength of the different applications in our industry for machine learning. So you can see, for example, drilling is one of the biggest ones, but reservoir also is an important one. So what I'm going to talk about today are three separate topics in reservoir engineering in which machine learning has been found to be useful. On the right is some of the individual methods, the algorithms that have been used. I won't talk about them in great detail, but there are some points to discuss in the way that the algorithms are actually applied. So let me begin with the first one, which is permanent downhole gauges. They have been used for 20, 25 years in our industry already. More than 20,000 have actually been installed worldwide, which seems at first like a small number, given that there are more than 1 million operating oil wells and gas wells in the world. However, given the fact that permanent downhole gauges are installed in the highest value wells, I would sort of guesstimate that perhaps half of the world's oil and gas actually flows to the surface past a permanent downhole gauge. So they are a significant vision for us of the producing oil and gas deposits of the world. Nonetheless, those gauges are typically not placed for the benefit of the reservoir engineers. They're placed for the production engineers to monitor their equipment, etc. And although we do use the data for reservoir analysis, we don't use it as much as you might imagine. And there are a few good reasons why. One of them is shown in this sample of a record from a gauge. This is a gauge that actually measures both pressure and flow rate. And this segment of the record is about 2 minutes long. So this device measures once per second pressure in dark blue and flow rate in pink. And you can notice, first of all, that the data appears to be very noisy. That's one of the characteristics of permanent downhole gauge data. But what I would emphasize in here is you can see that at the point A, the the flow began to increase and the pressure began to decrease. That's a reservoir response. But if you pay close attention, you'll see that for the most part, the pressure and the flow rate are going in contraindication. So when one drops, the other one goes the opposite direction. And that, of course, is also reservoir response at a very high frequency. At the point I've marked B, however, both the pressure and the flow rate drop at the same time. So actually that is noise. So importantly, in this signal, there is a lot of high frequency response of the reservoir to flow rate changes of the well that are recorded in the permanent downhole gauge. And there is also noise. So the mixture of noise and signal is a complication for the point of view of analysis. Were we to simply smooth out all of the noise in this data, then actually we would be throwing away a lot of high frequency reservoir response, which would be actually something we're quite interested in because it's the near wellbore region. So that relationship between pressure and flow rate is a pattern which is characteristic of the reservoir, and therefore it is a classic problem which is suitable for machine learning. The basic idea for machine learning is to explore patterns between and relationships between data signals. So in our case, the relationship between pressure and flow, and sometimes temperature as well. And in the machine learning field, the recognition of patterns is highly developed. So as an example shown here on the right, from the so-called Google brain, where they trained the algorithm to actually recognize objects or things in single frames of YouTube videos. So what we can all identify here is that that algorithm learned to identify cats in YouTube algorithms, which, as we all know, is a common subject of YouTube videos. What's important about this application to us, though, today, is that the algorithm was not asked to identify cats. It was asked to identify important things, and by itself, it learned to identify these things, which we all see to be cats. So that adds something to the capability of the algorithms to actually identify objects in advance without actually knowing what they are. They're not actually asked to be the target of the analysis. So from our point of view, excuse me, we would get data from the field, we'd train the algorithm to learn the relationships between them, and then we can actually observe the reservoir response without knowing in advance what it was and be able to make predictions based upon that learning. So this is a larger example of a permanent downhole gauge record. We do already use these kind of data in the industry, but in a particular way. So the most common application of these data to reservoir analysis today is to interpret the periods of time when the well is shut in. The flow here at the bottom, you can see there I've marked in boxes the shut-in period, and then the pressure record is used in the conventional build-up analysis method. If we do that, however, we actually only get small fragments of the analysis, just short segments. So we might have a 100-hour shut-in, for example, which gives us 100 hours of data that we could interpret in the normal pressure transient analysis manner. But the data themselves, the original data, may contain tens of thousands of hours of reservoir response. There's about 10,000 hours in a year, and these gauges are active for years at a time. So applying the machine learning methodology, if we learn the relationship between pressure and flow rate, or it learns, then we can predict any other response to any other flow rate. And in particular, if we were to ask what would the pressure response be if we had 10,000 hours of constant flow, that's like shutting in the well for a year, we can actually see what the response would be. So it gives us the capability of a vision of the entire data without the entire data having to be suitable, carefully shut in the way it would be for a wireline or conventional build-up test. And those of you who work in the field will recognize that that concept is one we've been attempting for a long time. It's known as deconvolution, to deconvolve the pressure flow rate signal and turn it into a simple pressure response. And what we gain in doing that by adding another 10,000 hours of data is we can see reservoir response that we could not see in the 100 hours of data. We can see the reservoir boundaries. So what we gain from machine learning is, first of all, to actually make use of data, which we quite often nowadays don't, and tease out of it the reservoir response from a complex history into a simple one. And I'm going to show you shortly. The point is that not only can we use the whole data set, but we can actually use the noisy data set without having to remove the noise in advance, which is actually one of the difficulties of the algorithms we use today, the algebraic ones. And finally, and most importantly, like the cat, we can reveal the reservoir model without necessarily asking for it in advance, without specifying what it's going to be. And to illustrate that, I'll show you, first of all, a synthetic example. This is an example in which the flow rate is actually one recorded from a gauge, but the pressure is generated with a specific reservoir model. So the data that were used to train the algorithm up on the top left, and after training on the top right, the graph marked B, is a recomputation of the pressure based upon a given flow rate signal. And actually, there are two lines there, red and blue. You can't easily see the difference because they overlay each other exactly. Importantly, what you notice is that in the period after the well goes back into production again, the algorithm replicates the individual high-frequency wiggles in the signal. Those are not noise. Those are actually high-frequency reservoir responses. And we added noise artificially to the original. I mean, there was a noisy signal. We added additional noise, and basically the machine learning algorithm saw the underlying signal and not the noise that we added. Down the bottom right, what you can see then is the forecast or prediction of what any flow rate history might be. So we gave it a different flow rate history and predicted the pressure. And because we knew the reservoir model in this case, we can show that that was done correctly, red and blue overlying each other. And then finally, on the bottom left, what you see is a prediction of the pressure for a completely constant flow rate. And that, of course, is the deconvolution exercise, in this case shown in a pressure derivative plot that we would normally consider for pressure transit analysis. So that was a synthetic example. This now is a completely real one. These are real pressures and real flow rates. In this case, what we trained on the early part of the data, and then we predicted into the future. So it's not only predicting within the time frame of the data which was used for training, but also forecasting into the future. You can see it's a slightly imperfect rendition of the training data. However, in comparing to what we actually knew, but the algorithm didn't for the future, it's also a good rendition of that as well. Once again, we can do the deconvolution shown on the bottom left. We don't, in this case, know whether that's the true answer or not because these are real data. However, it emphasizes the fact that we're able to do that. So let me talk for a few moments about the way that particular algorithm works. This is a so-called feature-based method. That's sort of the traditional machine learning algorithms. The way that this particular algorithm works is called kernel ridge regression. the way effectively it works is to construct an output signal rendered here, called here in this equation X, that's the pressure basically, in terms of a selection, a relatively small selection of features. Q is the flow rate and T is time. And the algorithm assembles those features in whatever way it chooses to render the final response. Now, importantly, what you notice about this selection of features, which is provided, there's a direct relationship of the flow rate itself. There is a log time component, there is a time component, and there's a reciprocal time component. And we all know, of course, the fact that log time is one of the components of the solution, the analytical solution of the actual problem. So this is not using the analytical solution, it's making its own solution out of pieces from those features. And the reason I wanted to emphasize this in this equation is that a concern that people often have about database methods is that they like to make a distinction between database methods and physics-based methods. And what you can see here is that this database method actually contains physics. There's a whole lot of physics actually used by the algorithm in its operation. That isn't true of all database algorithms, but it is of this class of algorithm. So I made mention earlier on about the noise in the data. And permanent downhole gauge data has a lot of different kinds of noise. It's just regular noise, like I showed you already. But there are also outliers, and there can be simply just crazy segments where something was going on with the gauge. And the methods that are used traditionally for deconvolution, the algebraic methods, simply cannot accommodate those kind of variations. And that's true in general also of most history matching based methods, algebraic ones. And what they have a lot of clever methods of smoothing and removing noise, etc. However, the database methods are not so sensitive to noise. So to illustrate that, here is again a synthetic signal, so we can confirm the truth of the answer. So this signal contains both random noise as well as outlier noise that you see shown in pink. So these are data points which are suddenly, as much as 500 psi different from the trend. And those kind of signals actually do occur often in permanent downhole gauges, where you get a bubble of gas which blocks the port of the gauge for a couple of seconds and then blows away, something like that. They're a common observation in permanent downhole gauge data. The machine so that data basically could not be analyzed with analytical deconvolution methods, and yet the application of the same algorithm, feature-based machine learning method, can correctly deconvolve those data and reveal the underlying signal without removing the noise. The noise is actually left in the signal during the training. The algorithm learns that most of the data are response, and it basically ignores the noise. And all of you have used similar machine learning algorithms every day. When you do character recognition, for example, the algorithm is able to read the characters even though they might be out of focus or slightly distorted, as perhaps is my voice, and the algorithm on the bottom is translating into English and then Dutch. Now, we can go a little further with this idea. Permanent downhole gauges actually can typically measure pressure. Some of them also measure flow rate, the expensive ones, but not all of them do. So the kind of analysis I've shown you so far was looking at flow rate and pressure, but all gauges of any pressure gauges of any kind in our industry also measure temperature. And they do that to compensate the gauge. And this is a real record from a gauge which actually measures all three, pressure, flow rate, and temperature. I'm not showing the pressure. But all of you can see the strong relationship between flow and temperature. So the temperature, in fact, becomes a kind of a substitute for the flow rate in gauges which actually don't measure it directly. So in much the same way we analyze the pattern relationship between flow rate and pressure, we can also analyze the relationship between temperature and pressure. And using that same real data set I showed you before, this is now trained not on flow rate, but on temperature, and used to predict the pressure into the future, which, as you can see here, it does correctly, because actually we knew in this case what the future was. We can also do deconvolution. If we provide a temperature for a constant flow rate, we can actually do the deconvolution and find the reservoir behavior. Okay, so that was my first topic, and I should tell you that was the longest one, so don't worry about the time. So my second topic is flow rate reconstruction. Initially, I was showing you the prediction of pressure based upon flow rate and time. In this case, we're doing the opposite. We're taking the data from pressure and time and using it to predict the flow rate. And that, of course, is something we often want to do in our industry. So once again, I'm showing you a feature-based algorithm. In this case, the unknown X is the flow, and it's constructed of pieces of functions of pressure, log time, and time. So an example of that, this is actually a real record of pressure and flow rate, and we cut out a piece of the middle. So the algorithm is trained on the data which precedes and comes after the gap. And then having trained the algorithm, we use the pressure in the gap to calculate the flow rate in the gap. So what you can see now is that we were able to correctly, because we had the measurement in blue of the flow rate, the red is the prediction, we correctly predict the flow rate in the gap based upon the pressure gauge alone. So in that case, for example, if part of the flow rate record is missing, we can fill it in based upon the pressure gauge. And I'll show you here the first of three real field applications of these algorithms. In this particular case, it's of the algorithm I just showed you. So you don't see the time or pressure scales in these records because these are real data that belong to a real company. But this record on the right, the amount of data which was actually used is 2 years in length. And shown up on the top is about 30 days of that segment. So the data in the red box, that's the 30 days, was used to train the algorithm. It's shown larger at the top, of pressure and flow rate. Now, I should tell you a story about this well. This is a well and an offshore platform which was drilled through the main reservoir into a new reservoir which underlay it. And therefore, this well was of very prominent importance to the company because it was the one well showing the behavior of the new reservoir. So for that reason, they had a single multi-phase flow meter on the platform, which they connected to this well most of the time in order to see what it was doing. However, on a regular basis, once a month or so, they had to divert the flow of all of the other wells in the platform through the multi-phase meter in order to keep inventory of their productions too. So this important well had gaps in its history because the multi-phase flow meter was being used in other wells of the platform. So the record that you can see down here at the bottom appears to have quite a lot of sections in which the flow rate is registered as 0. It wasn't actually 0. It was simply not recorded because the flow rate was being used elsewhere. But based upon the 30 days, actually the first 30 days when the gauge was attached to this well, we trained an algorithm and then predicted the remainder of the 2 years of history. So it's only trained on the first 30 days, and shown in red is the prediction of the flow rate based only on the pressure gauge, which of course continued to record the whole time. So there are some genuine periods of shut-in where the well was actually flowing 0, but most of the 0 flow rates actually were filled in by the algorithm so the company could see what it was actually doing during the time when the data was not available. Okay, moving then to my third topic, which is separate coming out of the reservoir and looking at the wellbore itself. This is looking at learning the relationship between the downhole gauges, the downhole pressure, and the wellhead gauges, the wellhead pressure. And you can see here a record. This is actually 3 years of data. Again, the scale is removed. And it's apparent here that there is some relationship between those signals, as we would obviously expect. So what was done in this particular case, the algorithm was trained on the first 180 days or so of data, about 6 months, and then used to predict into the future. So in this particular case, we're predicting the downhole pressure based upon the surface gauge. So the downhole pressure was available for 180 days. However, after that, it was predicted. In this case, we actually had the data, so we're comparing the prediction to the real data. So that has two practical applications in the industry. Number one is, what happens if the downhole gauge fails, as you know they sometimes do. That would provide the capability for the downhole pressure to be continued to be registered based upon the surface gauge into the future. And you can see with this real data example, we were able to do that 3 years into the future correctly. Another way in which we can use this capability in a practical application is to continuously predict a downhole gauge pressure and then compare it to the actual downhole pressure that, if the gauge is still working. And as long as those predictions are the same as the measurement, we can understand that the reservoir and the well are continuing to sing the same song that they always have. However, if they begin to go out of agreement, that's an indication that something has happened. There's a collapse of a perforation tunnel, or something has started to happen differently in the well or the formation. Go and take a closer look at this well and consider some remediation. And I'll show you a third practical example, which is similar, slightly different to that. This is from an SP paper by Sankaran et al., who at the time were working for Anadarko. And this is a figure from their paper showing a record of 5 years of measurements. And in this particular case, they were doing something similar to what I just showed you. They were training an algorithm for the bottom hole pressure. In their particular case, they weren't so much interested in the pressure, they were interested in the productivity index, the PI. So from time to time, they measured the downhole pressure with a wireline. So actually, they shut the well in to do that. And then they trained the surface gauge as input data to predict the downhole pressure and hence the productivity index. And there are many points on this graph. Most of them are red. Those are the predictions from the machine learning algorithm. But in amongst them are blue ones, which were from time to time, the measurements that were made with the wireline gauge. And what you can see rather remarkably is that although there's quite a lot of scatter, overall, the machine learning algorithm was able to predict correctly the productivity index over a 5-year period, even though the well is actually worked over twice. You can see here they did a workover or a refracture and a second time over here. So it continued to be able to correctly predict the productivity index of the well. And this paper excited a lot of interest in the industry because of, this is actually the caption from the figure. They were able to actually predict the productivity index and show it to be correct without actually needing to shut in the well at all once they'd got the original training. So that, of course, is a huge advantage. It not only avoids the expense of the wireline operation, but it avoids the shut-ins necessary in order to conduct those tests. So the output of the well is therefore enhanced. So summarizing then the three subjects I've talked about here, in the first case, we're using training on flow rate to predict the pressure. And as I've shown you, the machine learning approaches are robust against noise and outliers and aberrations in the data. I didn't show you aberrations, but it works with that too. And it reveals the underlying reservoir model without having to say in advance what it is, which is what we would do with a history matching approach. It's also possible and very useful in some circumstances to actually substitute the temperature instead of the flow rate when the flow rate is not continuously available. In the second case, the flow monitoring, we're doing the opposite. We're using training on the pressure to predict the flow rate. And as I've shown you, we've used that algorithm to fill gaps in flow rate records based upon times when the pressure record was available. I haven't shown it to you today, but a similar application of those kinds of algorithms can actually do allocation well by well when the flow rate is actually measured only at the manifold, which of course is the common practice. And then finally, as I showed you from the example from Sankaran, the possibility of actually testing the well without shutting it in. And then finally, in the wellbore modeling approach, determining the relationship between the surface gauges and the downhole gauges allows for the possibility either to fill in data if the downhole data are missing, or to make an alert that the well is behaving out of pattern and it should be looked at more closely. So I will leave you with a final thought. I mentioned once before that a worry that many engineers and managers too have about data mining approaches or data-based algorithms is that they don't necessarily contain physics. And as I mentioned, I showed you before, they in fact do contain some physics, at least in the class of algorithms I showed you. Importantly though, others like neural networks don't contain the physics quite that explicitly. But I would point out that although we may not always explicitly include the physics, the data actually are caused by the physics. So in honoring the data, we do in fact honor the physics as well. Finally, also too, we don't have to imagine data-based methods as substitutes for physics-based methods. There's no reason we can't do both. We don't consider geology a substitute for geophysics. We actually do both in our reservoir analysis. And we, I'm sure, do and will do both data-based methods and physics-based methods into the future. So with that, I will thank you and invite your questions.
Thank you very much for this very interesting and engaging lecture. You proved that machine learning is becoming even more and more into our life. You were the first keynote speaker having this machine learning based subtitles as well, so showing some sort of indication that we are going to see this more and more. Without taking any more time, I'd like to give the stage to Sebastian. We already have plenty questions in the list. Please go ahead, Sebastian.
Yes, thank you very much, Hadi, and thank you, Roland, for the excellent talk. I do hope you can hear me. I had a problem with my microphone earlier. Can you hear me, Hadi?
We hear you. Yeah, so far, yeah.
Sorry about that. Yeah, so plenty of questions coming in. Start picking up with a question that relate to your last point, the data-driven versus physics-driven models. And I have the first one from Brandon Hartman. Asked, so the algorithm decided inverted commas used log t in its model. Was that not a decision of the user? The algorithm chose it along with other parameters, the best way to match the training data.
Yeah, so this is a good question. So the algorithm did not decide by itself to use a log time. So we provided that collection of functions based upon our understanding of the physics. So this is where the physics came in. So that particular class of algorithm, the features have to be specified in advance. And in some cases, that's a disadvantage of that particular class of algorithm. Other kinds of algorithms, the so-called deep learning methods now, the neural networks basically, do not require a pre specification of the functions, and they figure out by themselves what they want to include. They're not including log times, etc. specifically. They're just including whatever they choose to create by themselves. So that is a distinction between the feature-based class of algorithm and the neural network kind of class of algorithms, in which in some cases we provide the features, in other cases they provide the features by themselves.
Thank you. So continuing on along those lines, Poe Wang asks, can we say that the machine learning algorithm learned the combined mass conservation Darcy's law using the pressure flow rate data? And the question continues, are there some non-standard nonlinear terms that appear as a result of finding the best fit between model and data?
Yeah, so yeah, that's a good observation. The algorithm basically learns Darcy's law, that pressure goes up and flow rate goes down. And if the data are constrained only by Darcy's law, then that's all it will see. If, however, there are some terms that go beyond Darcy's law, it will learn those too. And that, of course, is the compelling distinction between sort of history matching based methods, which would just give it Darcy's law in a simulator, and an algorithm that can go beyond that. So non-standard methods would be learned as well.
Thank you. We have a question from Bill Rossen, one of our former speakers, commenting on a fascinating presentation. Does predicting downhole pressure from wellhead pressure depend on the distribution of phases? For example, gas fraction being roughly the same in the training data as in the predicted period?
Yeah, so this is the question: can the algorithm predict what it has never seen? And the answer is usually no. So that's certainly a limitation, and that's an example. For example, where I showed you where the well may go out of pattern. So it's no longer predicting the downhole pressure correctly because something has happened, the phase distribution has changed, etc., and therefore it should be, somebody should go and take a look at it. So it's completely true. For example, and this in fact is the reason why the database methods are not, you don't just forget simulation altogether, because, for example, with simulation, you can predict that water is going to be produced because you've got some reservoir model that has that geology and that physics within it, and the water is going to arrive, 1 year into the history of the well. That's something that the machine learning algorithm cannot learn because it hasn't seen water before. It doesn't know anything about water, and therefore it's not useful for that kind of prediction.
Okay. Going to switch gears now a little bit, and a couple of questions, more than just a couple of question rounds of timescales. So the first one is from Andres Valdez, again commenting, very nice talk. The short and philosophical question: assume you train your algorithm data in years, how confident are you to make prediction in decades or even longer?
Yeah, so this is sort of one of the big questions also, and one of the directions I think of a lot of people's research into this field. How far into the future can you predict? I showed you with real data that some circumstances where we use 6 months of data to predict in over 3 years. The other case, we use 30 days of data to predict 2 years. That's actually not quite true. We were using some measurements over those 2 years to predict another. I did show you an example earlier where we predicted as far into the future as we had used in training of the flow rate and the pressure. The rule of thumb that we use for history matching using reservoir simulation is that you can reasonably predict into the future as long a period of time as you had data in the past. So if you have 2 years of history in your simulation, you predict 2 years into the future. We predict more than that, but we have sort of an expectation that the first 2 years are likely to be reasonable. And that's probably true of data mining algorithms as well. I mean, there isn't philosophically a difference between the two. So I think it's likely that if we're talking about a strict prediction into the future where we don't know anything about the future, we can probably go as far into the future reasonably as we have data in the past.
Okay, that's really interesting. So staying on the topic of times, Romulo Cavallo asked, would you say using low frequency pressure, for example, daily features would hinder significantly our ability to predict the buildups? And he follows on with that. It's the wrong one. I had the problem recently, tried low frequency daily with series of regressors, X-trees, gradients, boosts, supported vector machines.
Yeah, so this is an interesting question. And of course, the algorithms can be time consuming sometimes. If you have data every second for 10 years, that's a whole lot of data. But that's actually a question which we looked in our research at Stanford, and others I'm sure have as well. If we have data every day, for example, then if there's a transient which takes 3 hours, obviously you would miss it. You would see it if you have data every second, but once a day you wouldn't see that 3-hour transient. However, over the course of a year or 3 years of data that you may have recorded, one data point may catch the transient 10% of the way through, and a different transient may catch the change 20% of the way through, and a different data point may catch it 30% of the way through. So in spite of the fact that we may have measurements only once per day, we can actually resolve changes of the reservoir response at times less than 1 day. And that sort of seems a bit paradoxical at first, but it's because of what I just said. We catch transients in our once a day look. We actually can see different parts of the transient that's taking place, given the fact that there are many transients captured in the normal pressure downhole gauge history. So we can see subscale variations.
Okay.
Not as well as if we measure them, but certainly we can see to a higher resolution than we actually measure.
Right. Shifting gears again a little bit, Jesse Nyokawi, and also thanks you for a great presentation. And he wonders, do machine learning methods for porosity permeability estimation, hybridized machine learning methods for porosity permeability estimation, do they help us to lead to the construction of more reliable static reservoir models and dynamic models?
Yes, so this is another very good application of machine learning and data analytics, which I haven't talked about at all today. I've been largely looking at time series data, but of course there is a whole other section of our field where people are trying to predict geology, location of faults, porosity, permeability, etc., as the question asks. So although I haven't talked about it today, there's certainly a rich field of research that is underway and actually already done in that category or that classification of problem as well. And it has, to answer the question directly, has usefully been done.
Thank you. So closing with, again, so a two-part question by Alexandros Danilidis. Thank you for a great presentation. Do you think that data-based methods could be used in the future to help us understand the underlying, comes part 2, physics interaction of complex systems, for example, thermal, hydraulic, mechanical, chemical experiments or models, inform the analytical physical formulation of such systems? So what can we learn about the physics of the system?
Yeah, so one of the, I don't know that we can necessarily learn it directly, but what we can easily learn is the fact that something is missing. So for example, if we have a simulator which is simulating flow but doesn't take account of geomechanical effects, for example, and it doesn't do an adequate job of predicting the history, where a data analytical algorithm does, that reveals the fact that there's something in the response which is beyond the physics that we had in the simulator. So the data-based algorithms would honor geomechanics and flow behavior and temperature or what thermodynamics or whatever may be in there. And in doing so, they don't say what caused the response, but they reveal the fact that there was a response there.
Thank you very much. So coming to the end of the webinar, so thank you everyone for the great questions. Apologies if I couldn't read off all the questions. And thank you, Roland, for the great talk again and answering the questions so diligently. And over to Hardy for some final words.
Yes, thank you again from my side also to everyone. I'd like to take the chance to announce our next speaker is Professor Rosalind Archer from the University of Auckland. Rosalind is the director of the University of Auckland Geothermal Institute. And actually she did her PhD with Roland, I guess some time ago. She's going to speak about data integration in geothermal reservoir modeling. And now please note, since we are having the pleasure and honor to host Rosalind from Auckland, we are gonna run our webinar 2 hours later. So next week, we are gonna run the webinar at 6 Central European time in the afternoon, which would be 5 p.m. British time and 9 a.m. California time. So folks in California have longer time to sleep. Ronald was up quite early today, so please remember next week we are going to be here at 6 p.m. Central European time. One last comment: we received a few videos, pitches by from about six colleagues for the New Year greeting and what they do, where they come from. We are going to release those videos in some way soon as well. So until next week, 6 p.m. Central European time, 9 a.m. California, West Coast, and 5 p.m. British time, please stay happy, healthy, and tuned, and have a great 2020, all of you, wherever you are, whatever you do. Bye.
Thanks everyone. Bye. Bye.